This lecture introduces equilibrium problems for acid-base chemistry. And we've been dealing with equilibrium constants, the strengths of acids, Kas, pH, and now we're ready to get into equilibrium problems. And the reason why we need to get into equilibrium problems is because up to this point we've been dealing with strong acids. Strong acids like hydrochloric acid completely break apart into H plus and Cl negative. And because they completely dissociate, they have, of course, tremendously high Kas. Their Kas are so high, okay, they approach infinity. Well, why? Because it's products over reactants. And because you have very little reactants remaining as this reaction essentially goes to completion, it goes forward. Very little comes back. You can really think of this as a minuscule type of equilibrium because it really goes forward, which means these reactants approach zero, which makes this number approach infinity or undefined. I'm not really sure. But the point being is that these Kas are large because there's low amounts of reactants left and high amount of products when this reaches its equilibrium point, which is favoring, of course, the formation of the products. Now, up to this point, like the quiz we've been taking, if I was to give you a concentration of hydrochloric acid, let's say it's 0.15 molar. Well, my friends in chemistry, 1.5 molar HCl will be the exact concentration of the H plus if HCl completely dissociates. So anytime I give you a concentration of a strong acid, that is the exact concentration of the H plus. Now, if I was to give you a weak acid, now weak acids do not completely dissociate, meaning they exist mostly in their undissociated state. So in this reaction of the bicarbonate ion, HCO3, -1, dissociates a little bit, not a lot, into the free proton, which probably gets gobbled up by a water to make the hydronium ion, H3O+, plus the, what? Its conjugate base, the carbonate ion. Now, this is an equilibrium more realistic than the strong acid, because the strong acid really just goes one way, completely dissociates. Here we have some back and forth, but weak acids, their Ka is going to be small, which means for a weak acid, the reactants are going to be larger number in terms of concentration than the products. Well, why? Because most of the bicarbonate ion is going to exist in this state and not the proton. Very little is going to go forward. It remains pretty much uncombined. And let's take a look at what I'm talking about because you need to really visualize this. Okay? For instance, if I have a beaker of HCl, what does that look like? It's going to look like the undissociated ions. You're going to see H pluses and Cl negative. Now, of course, we don't see them, but this is what they would be on a molecular level, undissociated ions. You'd be hard-pressed to find any HCl's that are not undissociated or separated. Why? Because it completely dissociates. So the concentration of the HCl matches exactly the H plus. Why? Well, because for every one HCl, one proton is dissociated. Now, if I've got a beaker of HCO3 negative, which is the bicarb ion, okay, and I'm drawing this simplistically without the water being around, in this case, because it's a weak acid, there's going to be more of the what? Undissociated ion. So we're going to see mostly this undissociated, stuck together weak acid. Very little, if any. Of course, there will be some. So we'll throw an H plus here, and we'll throw the conjugate base here. But for the rest of these, it's going to be undissociated bicarb ion. Very little, okay, is going to be undissociated. Whereas in this case, it's all undissociated. So this gives me more products. More products means a higher what? Higher Ka. Sorry for that. Okay, so higher Ka. which is right here. All right, so that's the basics. Now, what do I mean by all that? Well, if I give you a strong acid, all I need to do is take the concentration of strong acid, and I have the concentration of the protons of the hydronium ion, and I can take my negative log of this to get the pH. Okay, or I can do some work to get the Ka. But if I've got a weak acid, I cannot get my pH or my Ka directly through the concentration of the 0.3. I have to do an equilibrium. So in this question, I'm giving you 0.3 molar HCO3. That is not going to equal 0.3 molar H pluses. Why not? Because it does not completely dissociate. So figuring out how much this dissociates is what this problem is about. So we have to use our equilibrium problems. We have to do something called ice tables to work with weak acids in trying to figure out how much they dissociate. We don't have to do that with strong acids because we know that this initial concentration will be the concentration here. So let me explain. With an ice table, they call it an ice table because you usually do this thinking initial concentration, the change, and then the concentration at equilibrium. Okay? So initially, for my weak acid, I have a 0.3 molar concentration. And initially, I have a 0 H plus and a 0 here. Now, why zeros? Well, because initially, before this dissociates, that is actually how much I should have. And these should be equal because one of these breaks apart into one of these. Now, what's the change going to be? Well, obviously, if I'm starting with the acid totally together, how much is it going to break apart? Well, we know it's not going to break apart a lot because it's a weak acid, but it's going to break apart somewhat. So 0.3 minus something, it's going to go down a little bit. Some of this is going to dissociate. Now, if it was a strong acid, it would completely dissociate, and this number would go to 0. All right? 0.3 molar would become all of H plus, and you'd be minusing 0.3 molar, and this would be 0.3 molar, and that'd be easy. And that's why you don't need an equilibrium table. Here, it's going to come off a little bit. We're going to go forward a little bit. How much? We'll make that X. Now, how much this loses has to be exactly what this gains. Why? Because one of these makes one of these. And this should also be a plus X. Why? Because one of these makes one of these. It's a 1-to-1 ratio. How much I lose of this is equal to how much I gain of each one of these. Right? Lose one, gain one of each. That's why it's the same value. Now, in this problem, they want you to solve for the Ka of the acid. Now, the Ka of the acid, as we've talked about, is equal to the products, H plus, over the, also the other product, I'm sorry, is the carbonate ion, over the what? HCO3 negative. So all I got to do is find the concentrations at equilibrium and plug them into my law of mass action, and I can solve for my Ka. So I need to find what this X is because I'm trying to find at equilibrium. Because initially, when we're not at equilibrium, we have 100% of my acid, and I know this is going to reach equilibrium. The question is, how much will it lose and how much will this gain? What is the X? And the key to the entire problem is the pH. They gave you the pH to be 4.3. What does that equal? Well, that's the what? Negative log of the H plus ion concentration. Wait a minute. If I can convert this pH to the actual value that it represents as a real number, that's going to give me this concentration, which, by the way, must be the X. So, to go from a pH back to a real number, what do? We do 10 to the negative 4.30. Why? Because negative log from this number gets me this. This is a logarithm. So 10 to the negative. So let's write that little neater. So what I'm going to do down here is do 10 to the negative 4.30. That's going to give me the actual concentration. Remember, this is a positive exponent. Okay, base 10. So I do my calculator, because I can't do this one in my head yet. One day maybe, 4.30. So 10 to the negative 4.30 gives me my concentration of my proton to be 5.0 times 10 to the negative 5. What is that? That is my concentration of my H plus at equilibrium. 5.0 times 10 to the negative 5. Wait a minute. 0 plus x equals 5 times 10 to the negative 5. My friends, in chemistry, the x is 5.0 times 10 to the negative 5. The pH told me that that is the H plus ion concentration that this generated. My friends, in chemistry, the x is exactly how much was being gone or made. So 0.3 minus 5.0 times 10 to the negative 5. And this is plus 5.0 times what? 10 to the negative 5. And this is what? 5.0 times 10 to the negative 5. Again, why am I adding? Because this is losing something. So that x, that amount, and what do we say? This is a weak acid, so does it go forward very much? No, we only lose 0.00005 of this concentration as we go forward. We only make 0.00005 of these two. It barely changes. So let's put the equilibrium concentration. So 0 plus 5.0 times 10 to the negative 5 is 5.0 times 10 to the negative 5. And what's the concentration here? What's 0.3 minus 0.00005? Well, I hope you can see that this number is so small compared to this number, it's insignificant. So this number stays approximately 0.3, and you can make that approximation. I mean, you could subtract it, and you can get some number that's smaller, but it's not going to significantly change your answer. Why? Because the Ka is so small. So my friends, in chemistry, I have the concentrations of my components. All I have to do now is plug them in to my equilibrium expression, and I can find my Ka. All right, so let's do it. So I have 5.0 times 10 to the negative 5 times what? Well, times 5.0 times 10 to the negative 5 all over 0.3 minus this number, or just 0.3, because this number is not going to change significantly. And you can make that approximation. So how do you do this? Well, we'll square the top numbers, and then we'll divide by 0.3, and I get a number that's approximately 8. We'll do 8.4 times 10 to the negative 9. And that is my answer. That is my what? That is my Ka. That Ka is tiny, which makes a lot of sense. This barely goes forward, which means if we started with 0.3, only a little bit does what? Comes off. Only a little bit is made. Okay? And that's how we do that type of problem. Now, calculate the percent ionization. How do I go ahead and do this? Well, percent is part over total times 100. So my friends, in chemistry, I have 0.3 molar, right, of the total acid. How much came off? There it is. Only 5.0 times 10 to the negative 5 came off. It's mostly undissociated. So let's do the percentage. So 5 times 10 to the negative 5 divided by 0.3 times 100. And this gives us 0.017%. Only that percent, or that's the percent ionization, which means That is the percentage of HCO3's negatives that actually do dissociate into its proton and its conjugate base. That is a small percentage. That's why it is a weak acid. Weak acids barely dissociate. What would be the percentage if it was a strong acid? It would be approximately 100%. Okay? Now, let's go through this. This question. Now, this question is very similar. Here they want you to calculate the pH, and this is the more important question of the two, I think. If I gave you what? HCl and said it was 0.3 molar, you would say, hey, the H plus ion concentration is 0.3 molar. And you would do the negative log and we'd be done. And we would do, go back on our ponies and ride all day. But my friends in chemistry, this is a weak acid. This is vinegar. And it's a weak organic acid. It does not completely dissociate. And if it did, okay, oil and vinegar would be deadly on a salad. Okay? Not only that, your salad would probably be mush as it's soaked in strong acid. Okay. Any case, so I have this called acetic acid, and I know it's going to dissociate into H plus and the conjugate base C2H3O2 negative, and I want the pH. I have to do an equilibrium problem because I need to figure out exactly how much this dissociates. They're giving me the Ka this time. All right, so watch how I go about this business here. In the other question, you solve for the Ka, you figured out the equilibrium concentrations, and then you plugged it in to your expression. Here, I'm going to have to solve for the equilibrium concentration. So watch what I do. Here comes my ice table. Okay, here comes my initial concentration, my change, and then my final equilibrium. So initially, I have 0.3 molar concentration of my acid. I have 0 of this and 0 of this. Why? Because before it dissociates, we're assuming initially before it dissociates and reaches equilibrium, we have 100% of this undissociated acid. Now, what's the change? Well, as it reaches equilibrium, it's going to go forward a little bit. We know the Ka is small, which means it's not going to go forward that much, but we know it's going to go forward somewhat. So what's the change? Well, the change is this is going to be minus x. We're going to lose something. Why are we going to lose something? Because it's going to go forward a little bit, not a heck of a lot. This is going to be plus x again. And this is plus x. Why are these both the same plus x? Because they are a one-to-one. For every one of these that breaks apart, you make one of these and one of these. So how much this loses is exactly how much this gains as it goes forward a little bit as it reaches equilibrium. Now, in the other problem, they gave me the pH so I could have figured out what this x was. Here we don't have that. So our equilibrium is going to be 0.3 minus x, and this is going to be, well, 0 plus x is x, and 0 plus x is x again. Okay, let's put in our Ka. Our Ka is equal to what? Our products over reactants, H plus, HO2, the acetate ion is our conjugate base, over our undissociated acid, our acetic acid, or hydrogen acetate. So what are we going to do here? Well, we're going to solve. We're going to plug these values in. And I'm going to solve for x. And I can do that because I know the Ka is 1.8 times 10 to the negative 5. Well, these are both x's. So x, x. Now, 0.3 minus x. Now, if we went this route and I kept this way, we'd come up with a quadratic formula, which would take us a long time to solve and would give us a lot of effort to solve for a number that's not going to help us. Isn't this x going to be very small because this Ka barely dissociates? And the answer is yes. Because we barely go forward, compared to this number is so small compared to this number, it's not going to change this number. Didn't we kind of approximate up here? Yes. So we're doing it down here. So we're going to get rid of this x because it's going to be smaller, so much smaller, it doesn't change this significantly, and we get good results. So this becomes 0.3. Without it, you're going to wind up having a quadratic or a binomial happen, and you'll need the quadratic to solve it. So simplification, 1.8 times 10 to the negative 5 times 0.3 equals x squared. So going further, 1.8 second EE, don't like the caret key, and I'm going to times that by 0.3, and that gives me 5.4 times 10 to the negative 6, and this is x squared. So what do you think I'm going to do to solve for x? Take the square root of both sides, and this is going to give me x equal, now I'm going to do the square root of 5.4 times 10 to the negative 6 at some point here, and I get 0.0023. Compared to 0.3, 0.023 is insignificant. As you can see, it's kind of approaching it, but we can still get a good answer. So what is the pH? Well, we just found the x to be this value. That's our concentration. That is our concentration. So it's 2.3 times 10 to the negative 3. We just found the x, which is the H+. What did the question want? It wanted the pH. Well, now that I just found the what? The H+ ion concentration, right? The H+ ion concentration equals this number that we just solved for at equilibrium. To find the pH, I'm just going to do the negative log of it. So negative log of the H+ ion concentration, which in this case is negative log of 2.3 times 10 to the negative 3. Let's do that. Negative log of that. I get a pH equal to, the suspense is killing us, 2.6. And that's the answer. A lot more work had to be done to figure out the pH in this case, because I had to figure out how much it would break apart, because it doesn't completely break apart. Its Ka is so small. And of course, the last question is, okay, calculate the percent ionization. Well, how do we do that? Well, total is 0.3. How much did it break apart? 0.0023. So we take our 0.0023 divided by 0.3, times it by 100, and we get, lo and behold, times 100 here, I'm running out of room, and this gives me, let's make it a different color, magenta. It gives me 0.77 dissociated. So this acid dissociates only 0.77% of the time. Notice its Ka is 5.4 times 10 negative 6. Look at the other one. It dissociated 0.017% of the time. Okay, so you can see that this makes a lot of sense, because the Ka for this top acid was a lot smaller, which means it barely dissociates, 0.017. This Ka for the second acid was 1.8 times 10 to the negative 5, much bigger. Therefore, there was what? More dissociation. Okay, but still, collectively, we're not even breaking apart into 1%. Okay, this is almost 0.02%. So this weak acids barely dissociate, and that's why we need equilibrium problems. Thank you, and good night.